Tech in 5.
Python in practice, master real-world projects in 5 minutes. Build a simple neural network with PyTorch. Let's dive in. PyTorch is a powerful and flexible deep learning framework that's perfect for both beginners and experts. In this video, we will build a simple neural network using PyTorch. We'll cover setting up our environment, creating a basic neural network, and preparing our dataset. By the end of this video, you'll have a solid foundation to start building your own neural networks. Let's get started. In our previous video, we set up PyTorch in a Docker container and performed some basic tensor calculations. Now, let's dive into the core of today's tutorial, building a simple neural network using PyTorch. But first, what exactly is a neural network? Imagine it as a complex web of neurons, similar to the human brain, designed to recognize patterns from data. It learns from vast amounts of examples, making it incredibly powerful for tasks like image recognition, language processing, and more. At its heart, a neural network consists of layers, and each layer is made up of nodes, or neurons, which are connected by synapses. Each connection carries a weight that adjusts as the network learns from data. Let's define our network. We'll start simple. A basic feed-forward network with an input layer, one hidden layer, and an output layer. In PyTorch, we define our model as a class that extends NN module. Inside, we define our layers in the init method, and how they connect in the forward method. There are 3 key components defined in the init method. An input layer that takes 784 features and feeds them into 128 neurons. A ReLU activation function in the hidden layer to introduce nonlinearity, and an output layer that maps the 128 neurons to 10 different output classes, suitable for tasks like digit classification. The forward method sequentially processes the input data X through the neural network. First, it passes through the input layer, then it is activated by the ReLU function in the hidden layer, and finally, it moves through the output layer to produce the final predictions. This setup is what we call a feed-forward network, where the data moves straight through from input to output. It's a solid starting point for most neural network applications. To train our neural network, we need data. Let's load the MIST dataset, which contains thousands of handwritten digit images, a perfect starting point for our training. First, we'll import the necessary library from PyTorch and load the MIST dataset. PyTorch provides a handy way to download and load this dataset directly through its Torch Vision package. We also applied a transformation to not only normalize the images, which helps speed up the training by scaling the pixel values, but also to flatten each image into a single vector. This ensures that the neural network can process the data effectively, learning from each image as a straightforward input vector. With our neural network defined and our dataset loaded and pre-processed, we're ready to dive into the training loop. This is where the real learning happens, as we feed the prepared data into our model to begin the training process. First, let's bring our model, SimpleNet, into the picture. Next, we define our loss function, which measures how well the model's predictions match the actual labels. For our classification task, we'll use cross-entropy loss, a standard choice for problems like this because it effectively handles multiple classes and penalizes incorrect classifications. To help our model learn more effectively, we need an optimizer, which adjusts the model's parameters to minimize the loss function. We'll use the Atom optimizer, known for its efficiency with large datasets and complex structures. Atom is favored for its adaptive learning rate, which means it adjusts how much the weights are updated during training based on the data, helping to speed up the learning process and improve accuracy. Now, let's briefly explore the training loop, a pivotal component of our neural network's learning process. In this loop, our model processes data, calculates losses, and updates its weights through a technique called backpropagation. This iterative process is key to improving the model, as it learns from each batch of data to make better predictions over time. In our next video, we'll break down each step of this training loop in detail. Stay tuned for a deeper dive into making our neural network smarter.
Stay tuned for more videos on Tech in 5.